Good afternoon. Thanks to the organizers for inviting me. Until now, it's been a very interesting workshop. I prepared a talk that's largely a review, so I apologize to the people who are already working actively in active matter, but I thought maybe it wouldn't hurt to give some sort of review of dry active matter that organizes into flux, like the movie that was playing before I started. And this is work with a group that I'll call the active matter group in our department at Federal University of Minas Gerais in Belo Horizonte. So I don't have photos, sorry, but Anna and Leo are here. And Leo has a poster upstairs that you may have seen, and Anna will give a short talk tomorrow, right? And Thiago couldn't make it, but I'll mention his work anyway. So, wow, this is quite an angle to see things from. Maybe it's better to look at the screen. Okay, so you've heard already something about active matter. They're self-propelled agents, and I'll be interested in many body kind of systems, not in individual systems like run and tumble entities. So each has its own source of free energy that it uses to move around, but it can change its direction either randomly or due to some interaction with other such entities. And when there are many particles, of course, you can have organization. And since these systems are far from equilibrium, we can expect new kinds of organization in certain cases. So that's, from an abstract point of view, that's what's particularly interesting about active matter. Of course, there are many applications to biological systems and also artificial systems, but I won't discuss that in great detail. So we have different kinds of ordering that can characterized by scalar order parameters, tensorial in the case of pneumatics, for example, or polar. So in a minimal description, each particle, from now on I'll call these agents, whether they're birds or fish or whatever, they're just particles. So the particles are characterized at least by a position and a velocity, and the propagation of order depends crucially on movement, on these velocities, and in the cases that I'll be discussing, on alignment of the velocities. In the evolution, whether it's in the real world or in simulations, there's always some randomness, so we're talking about stochastic modeling, and now there's a question of which dominates, the noise or the ordering tendencies, so we can expect phase transitions between ordered and disordered phases, perhaps more than one ordered phase, and so on. Okay, so we've heard about dry and wet active matter. This talk is only to do with dry active matter. Wet means there are, the medium plays a role, hydrodynamic interactions typically through the medium, but I'm not going to discuss that. That's much more challenging. Okay, so we've seen some examples, starlings, bats, bees on the surface of a hive, locusts, that's quite a dramatic representation, fish, and so on. Oh yeah, little robots we heard a lot about. Nanopolar rods on a vibrating surface. So, okay, these are just examples. I'll borrow this text from Sriram Ramaswamy, who draws some important points about active matter, that each particle has its own source of energy, so it's self-propelled. It's different from having non-equilibrium systems that are somehow acted on from outside through a drive or through shearing. It's force-free in the sense, that the particle transfers momentum to the medium and vice versa, and the direction of motion is set by the particle itself, by its orientation, or in the case of inertia, some combination of inertia and the orientation of the particle, but not by an external, not by an external field, as would be the case in sedimentation or driven lattice gases, for example, another popular system of study in non-equilibrium physics. Okay, so, okay, we don't need, so what happens in the physics of active matter, right? Active matter, in large part, belongs to biology. Not easy to drink with a microphone in front of your mouth, but. We want to look at general, possibly universal aspects of what happens in active matter. That means study minimal models that just capture the essential details. And of course, we can use theoretical tools of statistical mechanics and stochastic processes, but much of what we know from equilibrium, we have to forget, or at least treat with a certain skepticism and not assume that it's going to be valid. Of course, a great deal of work is done using stochastic simulations, and hopefully at the end of the day we can have comparisons with quantitative experiments. So I'm going to focus on the VICSEC model, which I assume most of you have heard about, but perhaps not everybody remembers all the details, so I'll review that. I would call it the Ising model, or one of the Ising models of active matter, or is it one of the minimal models that's been studied in great detail. So they were looking at flocking, or the organized motion of entities that organize without following a leader, and that's the important point, that all of this is, if you want, anarchism, right? We have these birds that fly around, but somehow they organize without following a leader, and that's an important question, how that can happen. So they organize, obviously, in the presence of noise, and we can identify these familiar concepts from equilibrium phase transitions. An important point about this model in particular is that there's no excluded volume, but I'll come back to that later on. I forgot to set my timer. Well, okay. So let's go. So we have, for the moment, in the original model, a fixed number of particles in a 2D system with periodic boundaries. Each particle has a position and a velocity, and these will evolve in parallel in discrete time steps, delta t. This model in particular, because of the way it's defined, is not Galilean invariant, which is important for certain considerations, and the only conserved quantity is the number of particles then. Okay. So, they all move at the same speed as well. You see, we're getting more and more minimal. So there's a speed v0, and there's a unit vector that describes the direction of motion, which is also the orientation of the particle in this case. And in 2D, we can just associate that with an angle. There's an angle characterizing the direction of motion of each particle. And the point is that these angles are going to effectively interact in a kind of interaction that's reminiscent of magnetic systems. In fact, in one extreme case, you can think of this as a magnetic system, if you have excluded volume and the density is so high that no one can actually move, then basically you go back to a magnetic system. But of course, there's much more going on than that when the particles are allowed to move. So, so each one will tend to align its orientation and therefore its direction of motion with the other particles within a radius r0, right? A certain local region. And that includes the particle itself. So I have a particle at the center of this circle of influence, and all of these particles, essentially we calculate the mean direction, and then we add a noise, and that's going to be the new orientation or direction of motion. So here it is formally. First we update all of the angles from time t to time t minus plus delta t, taking this sum of this vector sum and finding what angle this corresponds to, and then adding a noise. So the parameter eta is the noise intensity. Xi is, these are a collection of independent, identically distributed random variables, uniform on minus pi to pi. So it covers the whole circle, and then eta determines the intensity of this noise. So the particles simply move along straight lines during this short period, and there's a reorientation. Of course, the conflict will be between this noise strength and this tendency to orient with the neighbors. The sum here is over the neighbors, that is all of the particles within a distance r0 of particle I. Okay, so I think I've covered everything. Arg will just be the angle that corresponds to this vector sum. Okay, so here it is in pictures. We start out with a particle and its neighbors. We look at the mean direction of motion within this circle of radius r0. We generate a new direction by looking at the direction of the vector sum plus a noise, as I've already mentioned. So that tends to align this particle with its neighbors. And then everybody moves along the direction of motion. Okay, so that's the Vicsek model, introduced in 1995. There are a bunch of parameters, but in fact you can set delta t and r0 to 1 without loss of generality. You still have these, you still have these three parameters to play with. And it's typical to use some value of V0 that's 1 or a half, or some convenient value. So basically, it's the conflict between density and the noise intensity. Okay, we have an order parameter. Here's just the vector sum of the orientations of all of the particles. Remember, S is a unit vector. And then the time average of this instantaneous order parameter is what we look at in terms of phase, ordered phase or disordered phase, and so on. Now, what happens is that there's an ordered phase. This is, let's say, an empirical fact or a simulational fact. And that's interesting because in a two-dimensional system that breaks a continuous symmetry like rotation, in equilibrium, long-range order in such a system is prohibited. It's prohibited by the famous Mermin-Wagner theorem. But since we're out of equilibrium, the conditions of validity for that theorem don't apply. And in fact, it is possible. This was analyzed in great detail by Toner and Tu, but I won't go into that discussion. But they perform a kind of hydrodynamic analysis and put this on a firm basis. So when Vicsek and his co-workers studied this model, their conclusion, based on simulations of small systems, relatively small systems, was that there was a continuous phase transition, a critical point, critical exponents, all of that phenomenology. But it turns out when you look at larger systems, as Ig and co-workers did a bit later on, that the transition is discontinuous. And the reason for that is formation of coherent structures that have a minimum size. So these structures, these so-called bands or shocks in the density profile, don't appear in small systems, and you're left with the impression that the transition is continuous. But in fact, it's a discontinuous transition. Here are some simulation data showing, I mean, these data in themselves are not sufficient to conclude that it's discontinuous, but at least you see some evidence. But then you look at probability distributions, hysteresis, a whole bunch of Binder cumulants, et cetera, a whole set of indicators that confirm that this is a discontinuous phase transition. Okay, so what happens, the global phase diagram in the noise and density plane is like this. You have for low densities and or high noise levels a disordered phase. Then in the opposite limit, you have an ordered homogeneous phase, but the transition occurs through this coexistence region where you have these high density ordered bands existing in a kind of vapor of low density disordered particles. Good. So with that said, in the remaining few minutes, I'll give a quick summary of what we're doing in our group at UFMG. So you may have seen Leo Sant's poster upstairs. If not, hurry to see it, because I don't know if it'll be there tomorrow. But he's looking at the same model, but with a population dynamics. This is a problem that was suggested by Ig, and we're doing this in collaboration with Ig. But the idea is that there's a birth and death process that creates and destroys particles locally, in a local process. So the death probability is proportional to the local particle density. In fact, we use the same value, R0, that you use to average the velocities. And it's, I would call it Malthus-Verhulst dynamics, not Malthusian, where it only grows. This grows and shrinks. But in any case, that's what happens. And as you can imagine, in the limit of very slow population dynamics, the behavior is quite similar to the original Vicsek model, but in the opposite limit, we see a smoothening. It's clear that the transition is not continuous, and in fact, it appears to be mean field-like. So here's one figure from these studies that Leo is doing. You see this parameter nu is like the mean time between population events. So the rest of the time it's just doing the normal Vicsek dynamics. And you see something that, again, looks like a discontinuous transition. Whereas for rapid population dynamics, there's some sort of phase transition, but it looks very smooth. It almost looks like it will converge to a mean field-like behavior, but that's not fully decided yet. Okay, moving on. Another project involves Vicsek model with excluded volume. And since we have excluded volume, it's very convenient to use a lattice gas representation, only one particle per lattice site. And we've restricted the particles to the sites of a triangle lattice. Of course, each site has 6 neighbors, but since we're minimalists, we've allowed only 3 directions for the particles to hop. which is enough for them to get around and visit all different places. And so, and there's also this neighborhood. This is our R0, right? There are 19 sites in this neighborhood, and that's the neighborhood that's used to update the orientation. And we find an interesting variety of structures that can appear. Perhaps the easiest to understand is the so-called mobile band, which exists at low noise levels with a vapor of particles in all different directions. So the vapor outside is disordered, and then we have this band in which particles are essentially blocked from moving forward, except at the boundaries where they can evaporate and recondense. But we find other kinds of condensed structures, like traffic jams of different kinds, 2 different traffic jams, mobile bands, and of course the disordered phase. So we're trying to sort out the phase diagram. Here it's changed. Noise is now horizontal and density is vertical. Sorry about that. But in any case, you see that for low noise, you have a vapor and some sort of condensed structure, which is either that immobile band or some other kind of condensed structure. And then finally, you move to the disordered phase. Okay, so that's all I want to tell you about Thiago's project. And finally, Anna Novaes, who will give a short talk tomorrow, is working on a mean field description of all this phenomenology in the Big model with excluded volume. So here's the first case. Naturally, we did the simple thing first, which is a spatially uniform case. And the only situation which is really pertinent to the system that I was just describing is full occupancy, density equal to 1. And then there's a discontinuous phase transition in this description. Remember, the 3-state Potts model in 2 dimensions has a continuous phase transition, but mean field theories predicted a discontinuous transition. It's a failing, let's say, of the mean field approximation. So there's a discontinuous transition. There's actually a hysteresis loop, but here we're only showing one side of the hysteresis loop. And then for smaller densities, naturally, the critical noise level gets smaller, as you would expect. But now Anna has gone on to the difficult task of studying these spatially non-uniform systems with their different kinds of condensed phases. So this is an example. These are different snapshots of a system that's extended along the direction perpendicular to the band. Along the band, it's basically independent of position, so we use a very small number of sites, 3 sites along the direction of the band, which is also the direction of motion. So this is the initial condition. And then at later times, in this particular case, you see that the band is stable. I'm sorry about this. I really have to be more careful. So in this case, the band has stabilized. It will continue like this for longer times. But using this sort of theory, which is obviously involves numerical integration of a collection of equations describing each cell in the lattice, we're able to map out the stability of this kind of structure. In another case, the initial band, in fact, gives way to a kind of traffic jam. The blue region are particles moving downward and to the left, and the green region, they're moving upward and to the left, or they would if they weren't blocked. So this is another stable structure that appears in this mean field analysis that includes spatial structure. So that's what Anna is doing, and she'll say more about that tomorrow. Okay. So this is a summary. You can see it's an emerging area. It has applications to biology and other self-propelled entities. There are new forms of organization or forms of organization that violate prohibitions in equilibrium. And okay, I've told you about this. And very quickly, I'll flash this up. Perhaps these slides can be available so that people who are interested can check these references. Here's the original article, of course, and I recommend highly this brief review by Francesco Ginelli that gives a very good overview of what happens in the VICSEC model, and then there are various other important review articles. Well, this isn't comprehensive, but this is what we used in a special topics course a few years ago on active matter. Okay, so with this, I'll thank you for your attention.
Thank you very much.
Yes, Carlos.
Hi. What would be the fast dynamics in our? What does it mean, fast dynamics?
Oh, you mean population dynamics?
No, you mentioned about some fast dynamics. I'd say in the VICSEC model.
Yeah, this.
Yes. What does it mean?
It's population dynamics. In other words, the particles are doing two things. They're adjusting their orientations and moving around. That's the VICSEC dynamics. Population dynamics is the birth and death process. So when I say fast dynamics, that means on this, more or less on the same time scale as the VICSEC dynamics, each particle is also being selected to either die or reproduce, make a copy of itself. So that's, yeah, it's fast or slow population dynamics in that sense.
What is the parameter? What is the meaning of the parameter delta in the POTS model, in the active POTS model?
Delta?
You include some small delta.
There's a delta T. I'm not sure.
Yes.
Or you mean in the mean field theory?
I'd say yes.
Yeah. Okay. No, there.
Yes.
What happens is
what means?
we start. You have to break a symmetry, in this case, to see a non-trivial result. And this delta is how much we favored initially, one of the directions, okay, because it's a numerical computation. If you just started out with all three populations, directions 1, 2, and 3, equal, it stays like that. But we know it's unstable below the critical noise value, so that's just to break the symmetry. You can also go the other way. So here it's like, we're looking at a minimal perturbation. You could also begin with all of the particles, let's say, in direction 1, and test the stability of it coming from that direction. So all of these transitions, in a sense, are spinodals. We don't have a free energy function, so we're looking at stability limits.
Do you use periodical boundary conditions?
Yes. In both directions.
Rotational effects can appear if you confine the season, right?
Yeah, I mean, we never thought of that, but I mean, you could imagine having some harmonic potential that contains everything. But then, I don't know, I think you would form below the critical noise level, you would form some group that's pushed up against the wall of the potential well. But I'm not familiar with studies of active matter that use a confining potential. It's an interesting idea.
Okay, so in the interest of time, let's think again.